A rare visitor from deep space is racing through our solar system at unprecedented speed, and NASA's latest data has left scientists questioning everything they thought they knew about cosmic visitors. 3I Atlas, the third confirmed interstellar object ever detected, exhibits characteristics so unusual that some researchers are considering the unthinkable. Could this ancient wanderer be more than just a natural comet? As we uncover its secrets, the implications for humanity's understanding of our place in the universe become increasingly profound and, honestly, pretty terrifying. The breaking discovery. On July 1, 2025, the NASA-funded Atlas Asteroid Terrestrial Impact Last Alert System Survey Telescope in Rio Hurtado, Chile, first detected an unusual object later confirmed as 3I Atlas. This interstellar comet was initially spotted at a distance of over 4.5 astronomical units from the Sun, activating alarms across the global astronomical community. Its detection marked the third confirmed interstellar object ever observed passing through our solar system, following 1I Oumuamua in 2017 and 2I Borisov in 2019. The initial observations revealed a hyperbolic trajectory with an incredibly high orbital eccentricity of 6.141, the highest ever recorded for any known interstellar visitor. Larry Deneau from the University of Hawaii's Institute for Astronomy immediately recognized that this wasn't an ordinary solar system object, but a rare visitor that had been journeying through space for billions of years. The object's incoming velocity of 58 kilometers per second relative to the Sun marked it as the fastest interstellar object ever detected, surpassing both Oumuamua and Borisov by significant margins. From the outset, astronomers recognized that 3I Atlas was fundamentally different, initiating a worldwide mobilization of observatories dedicated to tracking this cosmic traveler and unraveling its profound mysteries. The discovery story. Between June 25 and June 29, 2025, the Atlas system had been gathering precursor observations that would later prove crucial in understanding 3I Atlas's trajectory and properties. These pre-discovery images, retrieved from survey archives and including work by the Zwicky Transient Facility at Palomar Observatory in California, helped confirm the object's interstellar path. Sam Dean, an amateur astronomer, contributed critical early tracking data, noting that the comet's trajectory through dense star fields near Sagittarius made early detection extremely difficult. The object's path passed through crowded cosmic neighborhoods, where countless background stars created a celestial camouflage, explaining why it had escaped discovery earlier despite being in the inner solar system for weeks. John Tonry, principal investigator of the Atlas project, immediately coordinated with facilities across the globe to confirm the object's characteristics once it was detected. The challenge of identifying 3I Atlas stemmed from its approach through regions where most sky surveys don't venture due to the overwhelming stellar background. This cosmic game of hide-and-seek had been ongoing since June 14, 2025, when the earliest pre-discovery images show the object silently crossing space. The rapid coordination between professional and amateur astronomers from multiple continents underscores the unprecedented global effort invested in monitoring this mysterious visitor. A stranger in our midst. 3I Atlas exhibits characteristics so unusual they continue to baffle the scientific community and challenge our understanding of natural cosmic objects. Traveling at a staggering 61 kilometers per second relative to the Sun, it far exceeds the speeds of its predecessors like Oumuamua and Borisov, making it the fastest interstellar visitor ever recorded. Its brightness is particularly notable, with a distinct coma and tail forming as solar radiation heats its surface, causing ice sublimation that creates spectacular visual displays. David Jewett from the University of California, Los Angeles, noted that the comet's tail and dust emissions provide rare data about materials formed in distant star systems billions of years ago. Perhaps most puzzling is that its trajectory lies almost perfectly within the ecliptic plane, the flat disk where most planets orbit the Sun, an alignment with merely a 0.2% probability of occurring by random chance. This mathematical precision has prompted serious speculation about whether the object's path represents natural celestial mechanics or something far more intentional. The combination of unprecedented speed, unusual brightness, and statistically improbable orbital characteristics raises fundamental questions about whether 3I Atlas is truly a natural object, or represents something far more enigmatic that challenges our basic assumptions about interstellar visitors. the predecessors. So, to really understand the true significance of 3I Atlas, we have to take a look back at the two remarkable interstellar visitors that came before it, each bringing their own, well, unsolved mysteries. The first, 1I, Oumuamua, was discovered in October 2017 by astronomer Robert Warwick at the University of Hawaii. It immediately stunned the scientific community with its elongated cigar-like shape and honestly, its completely unexplained acceleration away from the sun, all without any visible signs of outgassing. This mysterious acceleration just defied conventional physics and sparked some pretty intense debate about whether the object could be natural or possibly artificial. Then, in August 2019, amateur astronomer Gennady Borisov discovered 2I Borisov from his observatory in Crimea. This one proved to be a more traditional active comet, showing the typical outgassing behavior you'd expect from solar system visitors. The stark differences between these two ancient travelers, one mysterious and possibly artificial, the other conventionally comet-like, have really intrigued astronomers worldwide and, more importantly, set important baselines for comparison. Mark Norris from the University of Central Lancashire has pointed out that 3I Atlas, being the largest and brightest interstellar object yet discovered, gives us unprecedented opportunities to compare and contrast with its predecessors. This growing catalog of interstellar visitors is finally starting to reveal patterns that could unlock secrets about the diversity, origin, and true nature of these cosmic wanderers from distant star systems. The cosmic journey. 3. I-Atlas's trajectory through our solar system, honestly, follows a carefully orchestrated path that gives us optimal opportunities for comprehensive planetary observation. The object will reach perihelion on October 29, 2025, getting close to the Sun at about 1.36 astronomical units, positioned just perfectly between the orbits of Earth and Mars for extended observation. At perihelion, it'll hit maximum speeds of nearly 68 kilometers per second, which really shows off the extreme velocities you get with interstellar travelers. Paul Chodas from NASA's Center for Near-Earth Object Studies has calculated that while the comet poses no threat to Earth, keeping a safe distance of at least 1.8 astronomical units, its path brings it remarkably close to Mars, Venus and Jupiter during its trip through the solar system. The precision of this trajectory is pretty striking. It allows close approaches to 3 major planets and provides optimal vantage points for studying inner solar system dynamics. Karen Meach from the University of Hawaii emphasizes that this close approach sequence is, honestly, an unprecedented opportunity to see how an interstellar object interacts with different solar environments and planetary gravitational fields. The object will pass just 0.19 astronomical units from Mars on October 3rd, followed by a 0.65 AU approach to Venus on November 3rd, creating a sort of reconnaissance pattern that seems almost deliberately designed for a comprehensive solar system survey, rather than just a random cosmic passage. A scientific goldmine. 3I Atlas, really represents an unprecedented scientific treasure trove for astronomers and planetary scientists who are studying materials from beyond our solar system. With an estimated diameter somewhere between 0.32 and 5.6 kilometers, it's significantly larger than previous interstellar visitors. That means it actually allows for detailed study of its composition, structure, and evolutionary changes as it interacts with solar radiation. The Hubble Space Telescope, operated by teams led by David Jewett at UCLA, has been tracking dust emissions and nuclear activity, revealing ongoing sublimation of ancient ices and continuous dust release from the object's surface. These observations are providing crucial insights into the comet's volatile content and primordial materials, likely preserved for over 7 billion years, predating our entire solar system's formation. Stephanie Malam from NASA Goddard Space Flight Center is coordinating advanced spectroscopic observations using the James Webb Space Telescope to, hopefully, identify complex organic molecules and unusual isotopic signatures that could reveal the object's stellar birthplace. Current analysis has already confirmed the presence of water ice, both as solid grains and vapor, along with hydroxide ions, suggesting a water-rich composition that's typical of objects formed in the outer regions of planetary systems. The ongoing research aims to characterize the complete molecular makeup, including potential carbon monoxide, methane, and complex organic compounds, offering rare glimpses into the chemical building blocks and formation processes of distant star systems. Unanswered questions. Despite intensive global observation campaigns, 3I/Atlas continues to harbor profound mysteries that challenge our fundamental understanding of interstellar objects and their origins. The object's precise nuclear size remains frustratingly uncertain because the surrounding active coma obscures direct measurements of the solid nucleus, which complicates crucial density and mass calculations needed to determine its true composition and internal structure. While spectroscopic analysis has confirmed the presence of water ice and organic compounds, the detection of other expected volatiles like carbon dioxide and carbon monoxide remains elusive, raising questions about the object's formation environment and preservation mechanisms during its multi-billion-year journey through space. Julia de Leon from Spain's Instituto de Astrofísica de Canarias emphasizes that the object's unusual thermal properties and outgassing patterns don't conform to standard cometary models, suggesting either exotic compositions or structural characteristics not found in typical solar system objects. Perhaps most puzzling is the object's remarkable preservation state. How materials billions of years older than our solar system could remain so well preserved and chemically active after eons of exposure to cosmic radiation and interstellar conditions. Some researchers are beginning to debate whether the object represents a completely natural phenomenon or exhibits features that might indicate artificial construction or enhancement, a possibility that would fundamentally challenge our understanding of what's possible in the cosmos. The alien question. The possibility that 3I Atlas represents humanity's first encounter with extraterrestrial technology has, sparked some pretty intense scientific debate and forced researchers to confront some uncomfortable questions about the object's true nature. Avi Loeb, who's Harvard's Frank B. Baird Jr. Professor of Science, has really emerged as the most prominent advocate for seriously investigating artificial origins. He cites the object's statistically improbable trajectory, its unprecedented velocity, and honestly, its unusual structural characteristics as evidence that, warrant extraordinary investigation. Loeb's analysis suggests that the mathematical precision required for 3I Atlas's path, which actually provides optimal reconnaissance opportunities while passing close to multiple planets, exceeds what we'd reasonably expect from random cosmic events. His Galileo project at Harvard has been mobilized to conduct systematic observations using multiple telescopes worldwide, specifically searching for signs of artificial construction or technological signatures. However, mainstream astronomers like Sarah Seeger from MIT and Alan Fitzsimmons from Queen's University Belfast urge extreme caution, emphasizing that extraordinary claims require extraordinary evidence and that natural explanations should be exhausted before considering artificial hypotheses. The scientific community now finds itself balancing healthy skepticism with the recognition that, if 3I Atlas does represent extraterrestrial technology, the implications for humanity's understanding of our place in the universe would be, revolutionary, and potentially terrifying in their scope and consequences. Observing the visitor. Astronomers across the globe have mobilized an unprecedented array of telescopes and instruments to study 3I Atlas as it journeys through our solar system, creating the most comprehensive interstellar object observation campaign in history. Major facilities including the Very Large Telescope in Chile, NASA's Hubble Space Telescope, and the revolutionary James Webb Space Telescope are collaborating to collect multi-wavelength data that could, hopefully, unlock the secrets of this cosmic visitor. Michelle Bannister from the University of Canterbury notes that this coordinated effort involves over 50 professional observatories and, honestly, numerous amateur astronomers contributing observations and analysis. The Southern Astrophysical Research Telescope has been conducting detailed spectroscopic analysis to identify specific molecules and compounds in the object's coma and tail. Ground-based facilities like the Gemini Observatory and Keck Observatory in Hawaii are providing continuous monitoring of brightness changes, rotational periods, and thermal emissions that reveal internal heat distribution patterns. Canada, France, Hawaii telescope observations have captured deep images showing faint cometary activity even at great distances from the Sun. This international collaboration represents a new model for rapid response astronomy, with data-sharing protocols that allow real-time analysis and immediate follow-up observations when unusual phenomena are detected, ensuring that no critical information about this rare interstellar visitor is lost. Dawn of a new era. The detection and intensive study of 3I Atlas heralds the dawn of a revolutionary new era in astronomy, where interstellar objects transform from rare curiosities into, critical scientific targets that could reshape our understanding of galactic evolution and cosmic chemistry. Robert Jedica from the University of Hawaii estimates that technological advances, particularly the upcoming full operation of the Vera Rubin Observatory with its revolutionary LSST camera, promise to dramatically increase detection rates, potentially allowing astronomers to study dozens of interstellar visitors annually within the next decade. This technological revolution will create an unprecedented catalog of interstellar objects, providing statistical samples large enough to offer meaningful insights into galactic dynamics, planetary system formation processes, and the distribution of complex organic molecules across different stellar environments throughout our galaxy. Mark Norris from the University of Central Lancashire predicts that this growing database will reveal patterns in interstellar object populations that could answer fundamental questions about stellar evolution, planetary ejection mechanisms, and the chemical evolution of the Milky Way. As astronomers continue to unravel the mysteries of 3I Atlas and prepare for an influx of future interstellar discoveries, humanity stands at the threshold of a new cosmic perspective, one that will fundamentally transform our understanding of our place in the universe and the evolutionary history of our galactic neighborhood, potentially revealing whether we truly are alone or part of a larger community of cosmic civilizations. As 3I Atlas continues its mysterious journey through our solar system, it carries with it questions that could fundamentally alter humanity's understanding of our cosmic neighborhood. Whether this ancient wanderer represents exotic natural phenomena or, something far more extraordinary, the implications are honestly staggering. The coming months will be crucial as this interstellar visitor approaches its closest encounter with our sun, potentially revealing secrets that have traveled billions of years to reach us. Keep following InnoVision Tech for the latest updates on this developing cosmic mystery. Like, share, and subscribe. A decoded transmission from a visitor that has just entered our solar system confirms a chilling reality we've long feared. In the year 2025, NASA officials confirmed that the interstellar object designated 3I Atlas is not just a passing comet, it is broadcasting a message. What it says could, honestly, redefine humanity's place in the cosmos forever. Let's explore this together. The impossible visitor. What if our third confirmed interstellar guest wasn't just wandering through space but navigating it? When astronomical networks like Pan-STARRS first detected 3I Atlas in early 2025, it shattered every known classification. Unlike previous interstellar visitors, it was traveling at an unusually high interstellar velocity of 45 kilometers per second relative to our Sun, on a trajectory with a hyperbolic eccentricity of over 3.5. But it was its behavior that was truly impossible. It executed deliberate course corrections, moving with a precision that honestly defied any natural explanation. This wasn't a random rock. Its massive coma, a gas and dust cloud stretching 700,000 kilometers across, pulsed with a steady, repeating electromagnetic signal, unlike the chaotic outgassing of a comet like Hale-Bopp. The trajectory it took was impossibly efficient, using the gravitational wells of planets it passed as if it had a complete map of our system, a feat that takes our own probes years of calculation to achieve. The sheer energy required for these maneuvers, conducted without any visible propellant, suggests a technology that operates outside our known physics. As 3I Atlas carved a path through our asteroid belt with surgical accuracy, it became clear this wasn't an exploration, it felt like an arrival. When physics stopped making sense. There are fundamental laws that govern how objects move in space, but 3I Atlas seems to ignore them. Its trajectory showed a smoothness and efficiency that decades of astronomical observation say is impossible for a natural body. Scientists at NASA began using a term that honestly sent shockwaves through the community-piloted behavior. It executed a course correction amounting to a 15 meter per second delta V with no detectable outgassing, a feat that directly violates the Tsiolkovsky rocket equation for an object of its mass. Theoretical physicist Michio Kaku, when presented with the data, noted that the energy required for such a maneuver would be in the terawatt range, equivalent to the entire power output of humanity, sustained for several minutes. To a physicist, this is like watching a multi-ton boulder suddenly levitate and change direction in midair. The violation of this fundamental principle sparked frantic debates within institutions like the Jet Propulsion Laboratory, where teams ran millions of simulations and could find no natural model, not even an exotic outgassing of unseen material, to fit the observed data. This wasn't just an anomaly that stretched our theories, it was a direct contradiction of known physical laws. The object that defied reality. When NASA aimed the James Webb Space Telescope at 3Y Atlas, the data it sent back challenged our understanding of reality itself. The thermal readings were the first red flag. Instead of chaotic heat bursts, 3I Atlas showed a consistent thermal signature of 250 Kelvin, pulsing with a precision of microseconds. JWST's principal investigator for the observation, Dr. Jane Rigby, noted that the thermal stability was unnatural. Webb's spectrography then revealed hyper-reflective compounds that appeared artificial, a material with a near-perfect albedo of 0.98, reflecting 98% of all light, something not found in nature. But the most disturbing discovery was a faint electromagnetic pulse repeating every 147.13 seconds. It matched the signature of a real pulsar PSRB 1919+21, yet the object had no magnetic field capable of generating it. It seemed to be mimicking a signal, a form of cosmic camouflage. Webb's infrared analysis also found structural patterns resembling recursive geometric fractals, leading some to float the terrifying consciousness engine theory, comparing it to theoretical concepts like a Matryoshka brain, but on a smaller mobile scale. The combination of these impossible features in one object moves it from unusual to unequivocally artificial. Two visitors, one terrifying pattern. This wasn't the first time we'd been sent a strange message. The mystery of 3I Atlas deepened when researchers cross-referenced its electromagnetic signature with archived data from Oumuamua from 2017. They found the exact same 147-second frequency had been detected briefly in its tail. The difference was the signal strength. Oumuamua's signal was a whisper in the microjanskis barely above the noise floor, while 3I Atlas is broadcasting in the millijanskis, 1,000 times stronger. This really reframed everything. Harvard astronomer Avi Loeb's controversial theory that Oumuamua was an alien solar sail suddenly gained terrifying new ground. The statistical improbability of two interstellar objects separated by 8 years from different star systems, sharing such an unnatural signal is astronomical, suggesting they are part of a coordinated system. Oumuamua's brief weak signal now looks less like a random anomaly, and more like a handshake or ping to test for a response. Now 3I Atlas is answering with a full-blown data stream, implying the test was successful, and our civilization has reached a specific technological threshold. When space objects make calculated decisions. The moment we knew for sure we were being actively monitored was the moment it changed course. Just as scientists believed they had mapped its future trajectory, the Very Large Telescope in Chile recorded a subtle but unmistakable 0.05-degree inclination shift, an adjustment of 180 arc-seconds. This wasn't the random drift of a comet. The object veered off its projected arc, aligning with a new vector that brought it closer to Earth's orbital plane. To mission analysts like planetary scientist Dr. Sarah Seeger, the implication was clear: this was a conscious decision. The maneuver occurred just 72 hours after the James Webb Space Telescope began its focused spectroscopic analysis, a time frame confirmed by NASA's Deep Space Network that rules out coincidence. This inclination shift is an incredibly energy-intensive move, and the action wasn't just responsive, it was almost defiant, a clear message that said, "We see you watching us." The mood at the DSN's Goldstone complex as they tracked this impossible change in real time shifted from academic curiosity to profound alarm. Ancient mathematics from the stars. The signal wasn't just a pulse, it was a message written in the oldest language in the universe. Independent cryptographers analyzing the emissions discovered something extraordinary hidden within the narrow band, 0.1 Hz wide signal. They found precise mathematical ratios, the golden ratio, Fibonacci sequences, and prime number spirals. This is exactly what scientists like the late Carl Sagan predicted an intelligent signal would contain. The signal wasn't just a simple prime sequence, it was encoding the Riemann zeta function, a deeply complex mathematical concept related to the distribution of prime numbers. Furthermore, the signal's modulation, using a complex form of phase shift keying, corresponded to the value of pi to over 1,000 decimal places, an unmistakable beacon of intelligence. Frank Drake, creator of the famous Drake equation, would have seen this as a direct attempt to communicate not just presence, but profound intelligence. This wasn't a simple hello, it was a comprehensive intelligence test, broadcasted across the solar system for anyone smart enough to listen. Organic chemistry from beyond the stars. It wasn't just a machine, it was carrying the very building blocks of life. James Webb's detailed spectroscopic analysis revealed its outer shell was coated in complex carbon molecules, and its NIRSpec instrument found evidence of adenine, one of the 4 nucleobases in DNA, via clear absorption lines between 260 and 280 nanometers. What was alarming was the purity and organization of these molecules. Unlike the chaotic racemic mixture of amino acids found in the Murchison meteorite, the compounds on 3Y Atlas showed a 99.7% levorotatory excess, a homochiral signature that is a smoking gun for biological or artificial synthesis. Astrobiologist Dr. Heather Graham at NASA's Goddard Space Flight Center found the conclusion both thrilling and, honestly, terrifying. The terrifying implication is that if this is a seed ship, its purpose might not be benevolent. It could be preparing the environment for a subsequent colonization effort. The presence of DNA components suggests a biology that might be eerily compatible, or dangerously competitive, with our own. When Earth responded to the cosmic visitor. We thought we were only observing a distant object, but it was already interacting with our planet. A classified high-altitude surveillance balloon over Antarctica detected an extraordinary event. A powerful 500-megawatt tight-beam microwave burst at 23.4 gigahertz, lasting about 1.2 seconds, originating from the Amundsen-Scott South Pole Station's vicinity. The signal's timing aligned perfectly with another angular shift in 3Y Atlas's trajectory. Moments after the burst, seismic stations recorded ultra-low-frequency rumbles, registering a 1.2 on the Richter scale, but resonating at a perfect 0.0068 Hz, the exact inverse of the 147-second pulse. Dr. Francis Halzen, principal investigator of the IceCube Neutrino Observatory, later reported a statistically significant 3 sigma spike in TV-range neutrinos from the same location. The synchronization implies the Earth itself is part of a much larger ancient network that is now being activated, with a dormant relay station buried deep beneath the ice. The asteroid belt death run. Right now, 3I Atlas is navigating a cosmic minefield, and it's doing so with terrifying ease. Its current path takes it directly through the main asteroid belt, traversing the dense Kirkwood gaps at over 60 kilometers per second. Unlike most comets, which have highly inclined orbits, 3Y Atlas is cutting directly through the belt's core. Planetary defense expert Dr. Amy Mainzer, former principal investigator of the NEOWISE survey, noted that its 700,000-kilometer coma is interacting with millions of untracked objects. More astonishingly, minor course corrections have been observed, suggesting it's actively avoiding even meter-sized debris with impossible precision. This avoidance system must be processing the trajectories of over 1.5 million known objects in real time, a feat of computation that dwarfs anything on Earth. Its journey isn't a dangerous run so much as a demonstration of effortless superiority over a hazardous environment, adjusting its path by mere hundreds of kilometers to avoid potential impacts. Rewiring our solar system's neural network. This object isn't just passing by, it may be fundamentally changing the space around us. Data from NASA's Parker Solar Probe, led by scientists like Dr. Noor-e Rawafi, confirms the object is generating alpha waves in the solar wind, disturbances measuring several nanoteslas that can transfer energy over vast distances. Scientists at NOAA's Space Weather Prediction Center are concerned these disturbances could amplify the effects of the next coronal mass ejection, potentially increasing the resulting geomagnetic storm's KP index by 2 to 3 points, pushing it from a moderate to a severe event. The charged dust particles it's shedding are acting as charge carriers, creating a persistent conductive path between the object and the sun's magnetic field lines. It is essentially inserting itself as an active electrical component into our solar system's delicate circuitry. The long-term consequences for planetary magnetospheres, including the one that protects all life on Earth, are completely unknown and deeply concerning. The universe has sent us messengers and we are only just beginning to learn their language. The mysteries of Oumuamua and other interstellar visitors remind us that we are part of a vast, interconnected cosmos filled with wonders we are yet to discover. The journey into the unknown continues. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the frontiers of science. Thank you for watching InnoVision Tech. Imagine looking up at the night sky and realizing that something from another star system is silently racing past us at incredible speed. In the summer of 2025, astronomers detected exactly that. A mysterious visitor from the depths of interstellar space that has been traveling for millions of years before finally reaching our solar system. This cosmic wanderer, known as 3I Atlas, represents only the third confirmed interstellar object ever discovered. Today we'll explore everything scientists have learned about this extraordinary celestial traveler, and what it reveals about our galaxy. Discovery of 3I Atlas. Here's the moment that changed our understanding of interstellar visitors forever. On July 1, 2025, the Atlas telescope system at Rio Hurtado Observatory in Chile captured images of an unusual moving object racing through space at 61 kilometers per second. The Discovery team, led by Larry Deneau from the University of Hawaii's Institute for Astronomy, immediately recognized that this wasn't an ordinary asteroid or comet from our solar system. The object's hyperbolic trajectory and extreme velocity indicated it was following an escape path from our sun's gravitational influence. Initially catalogued as A11PL3Z, the mysterious visitor was positioned 4.5 astronomical units from the sun, approaching from the direction of Sagittarius. What made this detection particularly remarkable was that pre-discovery images dating back to June 14, 2025, revealed the object had been approaching undetected for weeks. The reason for this delayed discovery was its trajectory through the dense star fields near our galaxy's center, where countless background stars made it nearly impossible to spot against the crowded stellar backdrop. Within hours of confirmation, observatories worldwide began tracking this rare interstellar wanderer, setting the stage for one of astronomy's most significant discoveries. Atlas Survey System. But here's where this discovery became truly historic and earned its place in astronomical records. After extensive trajectory analysis by the Minor Planet Center, the object received its official designation as 3Y Atlas, where 3I signifies it as the third confirmed interstellar object in human history. This places it alongside the famous 1I Oumuamua discovered in 2017, and 2I Borisov found in 2019. However, 3I Atlas quickly distinguished itself from its predecessors in a remarkable way. Karen Meach from the University of Hawaii and her international team confirmed on July 2, 2025, that the object was displaying clear cometary activity. Unlike Oumuamua, which remained enigmatically inactive throughout its visit, 3Y Atlas developed a visible coma and tail almost immediately after discovery. Observations from the Nordic Optical Telescope revealed the comet was clearly active with a distinctive tail measuring at least 25,000 kilometers in length. John Tonry, principal investigator of the Atlas project, noted that this discovery validated their sky survey system's capability to detect rare astronomical phenomena. The rapid identification of cometary activity made 3Y Atlas the second confirmed interstellar comet, providing scientists with an unprecedented opportunity to study active sublimation processes in a visitor from another star system. Object classification and naming. Now prepare to be amazed by the sheer scale of this interstellar giant. Recent observations conducted by Marco Micheli from the European Space Agency using the Vera C. Rubin Observatory have determined that 3Y Atlas measures approximately 11.2 kilometers in diameter, making it significantly larger than both previous interstellar visitors combined. This massive size has profound implications for scientific study, as larger objects retain more of their original composition and provide clearer observational targets for detailed analysis. The comet's substantial nucleus is surrounded by an active coma that exhibits a distinctly reddish coloration, remarkably similar to what was observed in 2I Borisov. Daryl Seligman from Michigan State University, who led the initial characterization studies, noted that this color similarity suggests interstellar comets may share common compositional characteristics regardless of their stellar origin. The impressive scale of 3Y Atlas means it will remain visible to Earth-based telescopes for an extended period, giving researchers months rather than weeks to conduct comprehensive observations. This extended visibility window represents a golden opportunity for the astronomical community to gather unprecedented data about interstellar comet composition, structure, and behavior as it interacts with our sun's radiation and solar wind during its passage through our solar system. Orbital characteristics. Okay, here's something that will really blow your mind about this cosmic time capsule's incredible journey through space. Based on detailed orbital mechanics calculations performed by Davide Farnochia at NASA's Jet Propulsion Laboratory, scientists believe that 3I/Atlas actually originated from the Milky Way's thick disk region, where ancient stellar populations reside. This means the comet is potentially around 7 billion years old, which is, well, older than our entire solar system by approximately 2.5 billion years. Its epic journey likely began when gravitational perturbations from massive planets or maybe even close stellar encounters ejected it from its birth star system eons ago. For millions of years, this ancient wanderer drifted through the frigid vacuum of interstellar space at temperatures approaching absolute zero, which honestly perfectly preserved its primordial composition like a cosmic freezer. Sam Dean, an amateur astronomer who helped identify additional pre-discovery observations, contributed to tracking the comet's path backwards through time. The comet's trajectory suggests it has been traveling through the galaxy's spiral arms, potentially witnessing the formation and destruction of countless star systems during its incredible voyage. This preservation makes 3I/Atlas an invaluable scientific specimen, carrying within its frozen nucleus the chemical signatures and formation conditions that existed in a distant star system billions of years ago, offering unprecedented insights into galactic evolution and early planetary system formation processes. Physical properties. But here's what makes this discovery even more extraordinary: the unprecedented international scientific collaboration that made it possible. The research effort was spearheaded by Michigan State University's Darrell Seligman, who coordinated with a global network of observatories and research institutions to maximize observation time and data quality. Robert Warwick from the University of Western Ontario, who previously discovered 1I Oumuamua, provided crucial expertise in interstellar object identification and tracking protocols. The collaborative team included researchers from the European Southern Observatory, NASA's Goddard Space Flight Center, and the Harvard-Smithsonian Center for Astrophysics, really demonstrating how modern astronomy relies on rapid international cooperation. Grigory Fedorets from Queen's University Belfast contributed orbital dynamics expertise, while Tony Farnham from the University of Maryland provided cometary activity analysis. This coordinated effort represents one of the most comprehensive rapid response campaigns in astronomical history, with over 50 professional observatories and numerous amateur astronomers contributing observations within the first month of discovery. The team's ability to quickly organize this global response ensured that critical early observations were captured before the comet's activity levels changed, maximizing the scientific return from this rare interstellar visitor and establishing new protocols for future interstellar object studies. Comet activity features. Now let's trace the incredible path this ancient wanderer will take through our solar system over the coming months. 3I/Atlas will reach its closest approach to the Sun, called perihelion, on October 29, 2025, at precisely 11:41 Universal Time. At this crucial moment, it will be positioned 1.36 astronomical units from the Sun, that's about 203 million kilometers away, perfectly situated between the orbits of Earth and Mars. This optimal distance means the comet will experience significant heating without being destroyed by extreme solar radiation. During its approach phase, the comet will have several notable planetary encounters that provide unique observational opportunities. On October 3, 2025, it will pass just 0.19 astronomical units from Mars, only 28 million kilometers away, potentially allowing Mars-based instruments to conduct close-range observations. Following perihelion, the comet will swing past Venus on November 3, 2025 at a distance of 0.65 astronomical units. Most importantly for Earth-based observers, our planet remains completely safe throughout this cosmic dance. The closest 3I/Atlas will approach Earth, is 1.8 astronomical units on December 19, 2025. That's about 270 million kilometers away, providing excellent viewing conditions while maintaining a comfortable safety margin. This trajectory offers astronomers multiple observation windows from different vantage points throughout the solar system. Amateur contributions. Here's where the scientific excitement reaches its peak: the detailed analysis of this interstellar visitor's composition and structure. Spectroscopic observations conducted by Alan Fitzsimmons from Queen's University Belfast using the Gemini Observatory have revealed that 3Y Atlas is composed primarily of water ice, silicate minerals and organic compounds similar to comets in our own solar system. However, the presence of exotic isotopic ratios in its gas emissions suggests formation conditions significantly different from our local environment. Bin Yang from the European Southern Observatory detected unusual concentrations of deuterium-rich water vapor, indicating the comet formed in an extremely cold environment around a different type of star. As the comet approaches the Sun, increasing solar radiation is causing accelerated sublimation of volatile ices, revealing deeper layers that have remained frozen for billions of years. Jacqueline Keene from Boston University has identified traces of carbon monoxide and methane in the comet's tail, providing insights into the chemical conditions of its birth star system. The James Webb Space Telescope, under observations led by Stephanie Malam from NASA Goddard, has been scheduled to conduct detailed infrared spectroscopy to identify complex organic molecules that might exist within the comet's nucleus. These compositional studies are providing unprecedented insights into star formation processes and the distribution of life-building molecules throughout our galaxy. Surface composition. But here's what makes this observation campaign truly revolutionary: the unprecedented coordination of space-based and ground-based telescopes working together. Paul Chodas from NASA's Center for Near-Earth Object Studies has coordinated orbital predictions that allow telescopes to track the comet with extreme precision. The Hubble Space Telescope, under the direction of Matthew Knight from the Naval Research Laboratory, captured high-resolution images on July 21, 2025 that revealed intricate details of the comet's coma structure and dust distribution patterns. Ground-based facilities including the Very Large Telescope in Chile and the Keck Observatory in Hawaii have been providing continuous monitoring of the comet's brightness changes and spectral evolution. Kwanzi Ye, from the University of Maryland, has been leading photometric studies that track how the comet's activity levels change as it approaches the Sun. The NEOWISE Space Telescope has been measuring infrared emissions to determine the comet's temperature distribution and internal heat sources. This coordinated campaign represents the most comprehensive study of an interstellar object ever conducted, with data collection continuing through September 2025, before the comet passes too close to the Sun for safe observation. The wealth of data being collected will provide material for scientific studies for decades to come, advancing our understanding of interstellar chemistry and planetary system formation processes. Interstellar object density. Now here's something that sounds like science fiction but is being seriously considered by space agencies worldwide. Atsuhiro Yaginuma, an undergraduate researcher working with Daryl Seligman at Michigan State University, is conducting detailed trajectory analysis to determine whether a rapid spacecraft mission to 3Y Atlas might be feasible. The challenge is enormous. Intercepting an object moving at 61 kilometers per second would require unprecedented propulsion technology and launch timing precision. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory has been evaluating existing spacecraft designs that could potentially reach the comet during its closest approach to Earth in December 2025. Such a mission would need to launch within months of the discovery, requiring massive international cooperation and emergency mobilization of space resources. Alan Stern, principal investigator of the New Horizons mission, noted that while technically challenging, the scientific payoff from getting close to an interstellar object would be revolutionary. A successful intercept could provide direct samples of materials from another star system, potentially containing organic compounds or even microscopic signs of extraterrestrial life. Even if a full intercept proves impossible, the research being conducted is advancing rapid response space mission capabilities and establishing protocols for future interstellar object encounters. The mere possibility represents a remarkable leap in humanity's ability to explore beyond our solar system. Origins and age speculation. Finally, here's the most profound implication of this discovery for the future of astronomy and our understanding of the cosmos. The detection of 3I Atlas, following Oumuamua and Borisov, is providing statistical evidence that interstellar objects are far more common than previously estimated. Mark Norris, from the University of Central Lancashire, has calculated that approximately one interstellar object larger than 100 meters passes through our solar system every year, though most remain undetected. Robert Jedicke from the University of Hawaii estimates that the Atlas survey system, with telescopes in Hawaii, Chile, and South Africa, will detect several interstellar objects annually as technology improves. The Vera Rubin Observatory, scheduled to begin full operations in 2025, is expected to revolutionize interstellar object discovery with its ability to scan the entire visible sky every few nights. Michelle Bannister from the University of Canterbury predicts that within a decade, we'll have discovered dozens of these cosmic wanderers, providing a statistical sample large enough to understand galactic dynamics and planetary system evolution. Each new discovery adds pieces to the puzzle of how materials and potentially life itself might be distributed throughout our galaxy. 3. I-Atlas isn't just a single remarkable discovery, it's opening an entirely new field of astronomy that studies the messengers traveling between star systems, carrying secrets from across the galaxy. From its ancient origins in the thick disk of our galaxy to its spectacular journey past our sun, 3I Atlas has revolutionized our understanding of interstellar visitors and the materials that travel between star systems. This cosmic time capsule, preserved for billions of years in the cold of space, continues to reveal secrets about distant worlds and the formation of our galaxy itself. As we track its departure back to interstellar space, we can only wonder what other mysteries await discovery. Like, share, and subscribe to InnoVision Tech for more cosmic revelations. Humanity's farthest messengers are about to fall silent, but a plan is already taking shape to send a successor. For nearly 50 years, the Voyager probes have been our eyes and ears in the void, but their 1970s technology is fading. Now scientists are designing a true interstellar explorer, a robotic probe built to fly faster, see clearer, and journey deeper into the cosmic ocean than ever before. This is the story of the mission to build Voyager's heir. Let's explore this together. The original Voyager achievement. Ever wonder how two probes from the 1970s became the greatest explorers in human history? The answer is a mix of brilliant engineering and perfect timing. Managed by the Jet Propulsion Laboratory, Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare planetary alignment that happens only once every 175 years. This Grand Tour alignment allowed them to use gravity assists, slingshotting from one giant planet to the next. Under the guidance of scientists like the legendary project scientist Ed Stone, who served for 50 years, the discoveries were staggering. We saw active volcanoes spewing sulfur on Jupiter's moon Io, confirming 9 active eruptions and making it the most geologically active object in the solar system. We discovered the icy geysers of Neptune's moon Triton, a world so cold it spews nitrogen frost. These missions completely rewrote planetary science textbooks, all accomplished with custom-built computers that had just 69.63 kilobytes of memory, less than 1/1,000,000th of a single photo taken by a modern smartphone. They transformed our view of the outer planets from fuzzy telescope images into a detailed family portrait, revealing worlds more dynamic and complex than anyone had ever imagined. It was a mission of firsts, providing the data that forms the foundation of modern planetary science. The journey into interstellar space. But their planetary tour was just the first act. Once their primary mission ended in 1989 after the Neptune flyby, the Voyagers just kept going, beginning the Voyager Interstellar mission. Powered by their radioisotope thermoelectric generators, they traveled onward toward the boundary of our solar system. That boundary is the heliopause, the edge of the vast magnetic bubble our sun creates called the heliosphere. In August 2012, Voyager 1 finally crossed that boundary at a distance of 121 astronomical units, or 11 billion miles from the sun. The moment was confirmed by Don Gurnett and his team at the University of Iowa when the Plasma Wave System instrument detected the vibration of dense interstellar plasma, a 40-fold increase in density that sounded like a sudden tone in the data. It was the sound of leaving home. Voyager 2, which took a different route past Uranus and Neptune, followed in November 2018, crossing at a different point in our solar bubble and giving us a second, crucial data point. Right now, Voyager 1 is over 15 billion miles away, hurtling along at 38,000 miles per hour. This was a monumental achievement, marking the first time a human-made object had physically entered the space between the stars, our first tangible step into the larger galaxy. Current limitations of the Voyagers. Here's the fundamental problem. The Voyagers are technological marvels, but they are also relics. They were designed for the powerful environments of planets, not the subtle nuances of interstellar space. Their magnetometers, for example, were built to measure the powerful magnetic fields of gas giants, not the faint, tenuous fields between the stars. Their cosmic ray subsystem can detect energetic particles, but it lacks the sophistication to distinguish between different heavy elements with the precision a modern instrument could, which is critical for understanding the origin of these rays. Furthermore, their power source, which uses heat from decaying plutonium-238, is fading. The initial 470 watts of power has dwindled, losing about 4 watts of electrical power each year. To conserve what little energy remains, engineers on the ground are in a constant race against time, making difficult choices about which instruments to sacrifice next. Their data trickles home to the Deep Space Network at a mere 160 bits per second, meaning it would take over a week to send a single low-resolution photo. The signal is now so faint, billions of times weaker than a watch battery, that it requires the world's most sensitive radio antennas just to hear it. The case for Voyager 3. This is where the idea for a successor, which many call Voyager 3, becomes more than just a dream. While Voyager 3 isn't an official NASA name, it perfectly captures the spirit of a next-generation mission. The actual, formal concept being studied at the Johns Hopkins Applied Physics Laboratory for NASA is called the Interstellar Probe. Led by scientists like Principal Investigator Dr. Elena Provornikova, this would be humanity's first spacecraft specifically designed to explore interstellar space. Its entire purpose would be to journey beyond the sun's influence, born from the questions the Voyagers raised but could not answer. The goal is to build a probe that could operate for a minimum of 50 years and travel at a target speed of over 95,000 miles per hour. This incredible velocity would allow it to reach the heliopause in about 15 years, a journey that took Voyager 1 over 35 years. The mission's target isn't just the edge of the heliosphere, but a destination of 1,000 astronomical units into the truly undisturbed local interstellar medium. This distance is crucial because it's far enough away to be free from the sun's lingering influence, allowing us to sample the pristine material of our galaxy for the first time. Advanced technology capabilities. So what kind of upgrade would a modern interstellar probe get? Let me explain. Compared to the Voyager's 1970s technology, a new probe would be a revolutionary leap. Instead of limited sensors, it would carry a suite of advanced instruments, a plasma spectrometer, energetic particle detectors, magnetometers, and a dust counter, all with at least 100 times the resolution of the Voyager's equipment. Power would come from a next-generation RTG, designed for longevity and providing enough power to run a full suite of instruments for a century. But the real game changer would be its brain AI-powered autonomous systems. This would allow it to make its own decisions, acting like a true robotic field scientist. It could prioritize data, compressing less important information to save bandwidth for groundbreaking discoveries, and even react to unforeseen events without waiting for the 3-day round-trip communication with Earth. To achieve its speed, the mission would launch on the most powerful rocket available, like NASA's SLS Block 2, and perform a powered Jupiter gravity assist, using both Jupiter's gravity and an onboard engine to achieve velocities previously thought impossible for a long-duration science mission. The interstellar medium mystery. Why is this so critical? Because our entire solar system is hurtling through a cosmic ocean, and we barely know anything about the water. This ocean is the interstellar medium. Our sun's solar wind carves out the heliosphere, which shields us from about 75% of the most energetic galactic cosmic rays. This shield works because the solar wind's outward pressure physically pushes away this deadly radiation. But what is its true shape? For years we thought it was a comet-shaped teardrop. However, models by scientists like Merav Ofer now suggest it might be a sphere or even a deflated croissant. A key unresolved question is how the interstellar magnetic field drapes around our heliosphere, which is crucial for its structure and how it protects us. Our solar system is currently passing through what's known as the local interstellar cloud, a slightly denser region of gas and dust. An interstellar probe could tell us how this local weather directly impacts the shape and strength of our protective bubble. Understanding this interaction is fundamental to understanding our own cosmic environment. Scientific objectives and research goals. Let's get specific. What questions would a mission like the Interstellar probe finally answer? First, it would explore the unshocked interstellar medium, the pristine galactic material our sun is moving through. This means getting a baseline chemical inventory of our galactic neighborhood, the very stuff from which future stars and planets will form. Second, it would map the structure of our heliosphere in high definition, crossing key boundaries like the termination shock and heliosheath with far more advanced instruments. It would finally solve the mystery of its shape and reveal the physics of its interaction with the galaxy. Finally, the mission would journey to a target of 1,000 astronomical units from the Sun. As physicist Ralph McNutt from the APL team emphasizes, getting to this distance would allow us to look back and view our solar system as a complete astrosphere for the first time. From this vantage point, it could even detect the faint extragalactic background light without interference from dust in our solar system, opening a new window for cosmology and studying the universe's first light. It would be a multi-purpose observatory unlike any other. Practical applications for future missions. This isn't just about abstract science, it's about laying the groundwork for humanity's future in space. Let me explain. Any future attempts at sending probes to other star systems will require navigating the interstellar medium. An interstellar probe would act as a pathfinder, creating the first detailed atlas of the space just outside our solar system. It would quantify the radiation risks for future robotic or human missions, which would be impossible without the precise data this probe would gather. At speeds over 90,000 miles per hour, even a tiny grain of interstellar dust can strike with the kinetic energy of a rifle bullet. So the probe would map dust density to inform shielding design for future, even faster craft. Developing the technology to reliably communicate with a probe hundreds of AU away would push our deep space communication capabilities, benefiting all future missions. Furthermore, it would pioneer techniques for autonomous interstellar navigation, a requirement for any craft that travels so far from home that the sun becomes just another bright star. This is essential for concepts like breakthrough starshot, which would need this data to even begin planning. Cultural significance and golden record 2.0. What message would you send to represent all of humanity on a journey that will outlast everyone alive today? In 1977, Carl Sagan's committee assembled the Golden Records. An interstellar probe would carry on this legacy, but a Golden Record 2.0 wouldn't be a physical disc. John Lomberg, the artist who designed the original record's cover, has proposed a digital successor. This new archive could hold petabytes of data, the entire human genome, vast libraries of art and science, and perhaps even messages from the public. The new message would have to reflect our more globalized, digitally connected, and perhaps more self-aware civilization. The very act of creating it forces us to reflect on our collective identity and what we would want to say about ourselves to the cosmos. How do you represent humanity's flaws alongside its triumphs? Who gets to decide? This probe and its message will travel through the galaxy for millions of years, long after Earth has changed beyond recognition. It serves a dual purpose, a scientific instrument pushing the frontier of knowledge, and a cultural artifact carrying the story of humanity to the stars, a true monument to our civilization. Timing and opportunity. Here's the bottom line: if we want to do this, the clock is ticking. The Voyagers completed their grand tour because of a rare planetary alignment. To achieve the incredible speeds needed for this new mission, the interstellar probe would also rely on a gravity assist from Jupiter. The APL study pinpoints an optimal launch window in the early 2030s. The plan is to launch on a powerful rocket like NASA's Space Launch System and then perform an Oberth maneuver, firing its own engine at its closest approach to Jupiter to get the maximum possible boost. Missing this window could mean delaying the mission for another decade or more, waiting for the planets to once again align for such an efficient trajectory. A mission launching in the 2030s needs to be approved and funded years in advance, meaning crucial decisions must be made in the coming years. This is a generational opportunity, a symbolic passing of the torch to ensure humanity's boldest journey of exploration continues. It requires foresight and a commitment to science that looks beyond immediate returns, a gift to the future. An interstellar probe wouldn't just be repeating the past, it would be a quantum leap forward. It would push deeper, answer fundamental questions about our place in the cosmos, and test the technologies needed for future missions to the stars. The first Voyagers were our first messengers to the galaxy, carrying a hopeful greeting from a small distant world. This new probe could be our new voice, our new eyes, and our first true step beyond the sun's embrace. Are we ready to take that step? Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech.